So in this lecture, we continue to look at permutations of distinct objects, but the case 2, which is using distinct objects with repetition. So basically, if you have, say, the alphabets of the word rose as the objects, then you can use each of these objects multiple number of times when you are picking R objects at a time. So I'll just get next to the theorem, which is similar to what we proved for distinct objects without repetition. So the theorem goes like this, that the number of permutations of n distinct objects taken R at a time, where R again is between 0 and n, and the objects can be repeated, is n raised to power R. So we have to prove that the number of permutations of the distinct objects with repetition is n raised to power R. So again, I will just look at what happens when R is equal to, again, as part of the proof, we'll just go along similar lines, just do the case 1, which is for R equal to 0, and R equal to 0, as before, we just take it to mean that you don't do any rearrangement, you just take the permutation as it is. For example, if you had the objects in rows, you just keep them as it is, so it's just permutations are equal to 1. So you have n raised to power R. N raised to power R is also equal to n raised to power 0, which is equal to 1. So permutations for R equal to 0 are 1, and n raised to power R is also equal to 1. So therefore we have the trivial case of R equal to 0 proved. But we'll look at the other case, which is the more interesting case as before, which is, I'll call it case 2. R is greater than 0 and less than equal to n, and again we have to draw the boxes as before. I'll draw R boxes corresponding to R objects taken, like n objects taken R at a time, right? So we just need R boxes. So I'll just call them box 1, box 2, box 3, and box R as before. What is the difference now? The difference is that the objects can be repeated. So we have n objects, and then we have to fill in the R boxes using these n objects. So the first box, you have n choices, right? What about the second box? You still have n choices, right? Because you can use the objects with repetition, that is the key. So you still have n choices available even for 3, and so on for even the box R. So what is the value now for permutation? So permutations or arrangements of n objects taken R at a time, where repetition is allowed. It's clear from the fundamental principles of counting that you just have to take the product of all the choices for each of these boxes, right? So you just multiply n R times, right? Because you have n R boxes, so you multiply n R times, and this is equal to n R. So this has been proved again. So you notice that we don't have any notation like NPR for this particular uh, permutation. Like permutations where repetition is allowed, you don't have that compact notation like NPR, right? So this is not for repetition, only used when you cannot repeat the object. So we don't have any notation, but you just call it permutations of n. I should be clear, it's distinct objects taken R at a time where repetition is allowed. So let us cover some examples of using this in real problems, just like distinct objects with repetition and without repetition. If you solve the problems, I think you will understand the concept better. So we'll cover this problem now, which is the find the number of 4-digit numbers that can be formed from the digits 1 to 9, where the repetition of digits is not allowed and secondly the repetition is allowed. So you should be able to solve this problem. I'll give you the choices, and they are 3024, 6561. So first one is for not repetition not allowed, and second one is for repetition allowed. So you have 2421, 2422, and 6561, 4224, and 8578, and 2100, and 6561. So just try to solve this problem, and you should be already able to solve this problem looking at fundamental principles of counting, but just try to apply the formula which we covered for permutations and just solve this problem with that. So the correct answer is first one, 3024 and 6561. So let us look at the solution. First of all, we know that we have to use the digits between 1 to 9, so you can identify them as distinct objects, right? Because you have 1, 2, 3, 4, 5, 6, 7, 8, 9. And now the first one is the case where repetition is not allowed, and we have to make 4-digit numbers. So that means that it's same as if we were using this formula, permutations of n objects taken R at a time without repetition. Here it will be n equal to what, 9, right? Because you have 9 distinct objects, and how many, what is R? R is 4, right? Because you are forming 4-digit numbers out of these objects. So you will have R equal to 4. So we just have the answer as NP4, which if you go back to the theorem is same as 9 factorial divided by 9 minus 4 factorial, and you had 9 factorial divided by 5 factorial, and that will be same as 9 into 8 into 7 into 6, because 5 factorial will cancel out. And this is 3024. So you can note that this can be done using fundamental principles of counting too. Like if you had 4 boxes, I'll just draw 4 boxes, then you had the options 9, 8,
7 and 6, right? Because you had 9 options for the first box, 8 for the second, and 7 for the third, and 6 for the fourth. So you still have the product of the same numbers and you'll get the correct answer. This is just a compact way of representing the solution. So don't think that fundamental principles of counting is something completely different from permutations. It is. Permutations are based on fundamental principles of counting. Only thing is compact notation. So that's the only thing. Otherwise, fundamental principle of counting is fine as well. Okay, so that let us look at the second part, which is repetition is allowed. Again, here we had n equal to 9 and r equal to 4 because you are making 4-digit numbers. But here repetition is allowed, so the answer is just n raised to power r. So that is 9 raised to power 4. So it's just 9 into 9 into 9 into 9, which is 6, 5, 6, 1. So that is the answer. We just saw that. So again, in fundamental principles counting also, if you use 4 boxes to represent a 4-digit number, each box will have 9 choices and you get the same answer. So just try to understand the similarities and use whatever you want to use according to the situation.